Hello everyone, thank you for attending this virtual workshop. I'm Shuran, and today I'm going to talk about our work on learning visual representation for generalizable manipulation. So first, let's talk about what's visual representation and why they're important for robot manipulation. So here I'm showing you a typical pipeline of vision-based robotic system, where the system normally starts with some sort of raw sensory input that try to record the physical world, normally in the form of images or videos. And then the computer vision algorithm will try to convert the raw sensory input into a meaningful representation that describes the environment. And hopefully, this high-level representation can be directly used by the robotic system to perform actions such as grasping the coffee cup or walking around your home. So from this chart, we can see that the representation of the world is really the most critical part of the whole pipeline, because what the representation is determines everything else, from how you're going to process the sensory input to what kind of action you can perform. So for a very long time, the standard visual representation for robot planning was the result of 3D object detection or pose estimation. So this representation has motivated many planning and control algorithms that are designed on top of the full state information of the object poses. And similarly, it also motivates a big portion of computer vision research in 3D object detection and pose estimation, which also includes many of our own algorithms, such as the approach we used for the Amazon Picking Challenge in year 2017. So the task here is to build a system that's able to pick a variety of objects from a very cluttered bin or shelf and then put them into boxes in order to fulfill online orders. So at that time, we teamed up with MIT MCube Lab to participate in this challenge. So as you can probably imagine, our approach follows the exact classic pipeline, where our group from Princeton is in charge of the vision algorithm that try to infer the object pose from the LGBT image, and the MIT team are in charge of the motion planning given the object pose. However, this system does not work as well as we expected. So here are some major issues. So first is about the pose estimation accuracy. So even today, the pose estimation algorithm under heavy cluttered environment is still a very, very challenging computer vision task. And what makes it even worse is that the error produced by the vision algorithm will propagate to the planning system and result in failure execution. So for example, 5 centimeter error in computer vision might be very small, but may directly lead to a collision between the robot and the shelf. And the second issue is about generalization. So because the algorithm heavily relies on the 3D models of the object during training, the algorithm is very hard to generalize to unseen or new objects during testing time. So this approach reflects the limitations of a group of traditional methods that separately consider the perception and motion planning tasks. So in this talk, we will mostly focus on addressing the second issue, where the goal is to design a generalizable manipulation algorithm where the system is able to directly generalize to unseen objects without the need of a strong prior knowledge about objects, such as their 3D CAD model, predefined categories, and object poses. So to achieve this goal, in the second time when we participate in the Amazon Picking Challenge, we completely changed the system to directly predict the action affordance from the camera observation. So for example, the system directly predicts the suction point or grasping position directly from the LGBT image without the need of object pose estimation. So this is our final system in action. Because the system that no longer requires object pose information, it can easily generalize to new objects and is able to handle very cluttered environment. So this experience really tells us to think hard about what should be the right visual representation that can better bridge the link between perception and manipulation algorithms in order to make them more flexible and generalizable. So now we have this grasping algorithm. So does it mean that we are able to solve all the grasping problem? Well, unfortunately not. And here are examples of how you can easily break this system. First, since the system relies on calibrated the camera and perform open loop execution, the system will not work if you just slightly touch the camera, move the objects around, or raise the table height. And also, since the system can only perform top-down grasp, it will not work if you put the objects on a wall or shelf, which requires a different approaching trajectory. So if we categorize most of the recent work on learning-based grasping, here there's almost none of them is able to really achieve 6-step closed-loop grasping. The reason is that in an open-loop setting, the grasp problem is a lot simpler. Given an image of the environment, the system only needs to predict where and how to pick up individual objects. However, once you start to use the closed-loop formulation, every action the system takes will have effects on the state, which will drastically increase the possible state space the system needs to handle. And if at the same time we move from top-down to 6-step motion, we will also increase the corresponding action space. And together, the large action and state space will make the end-to-end learning extremely difficult. Therefore, to achieve 6-step closed-loop grasping, we really need to address two fundamental problems. First is how to get training data or to cover such a large space, and the second is how to design the state and action space to enable efficient learning. Here I'm going to talk about our recent work that's able to address these two problems and achieve 6-step closed-loop grasp. So first, let's look at the data problem. Many today's grasping algorithms choose to use self-supervised learning as a way to easily get training data. The problem with this is that this setup only works for simple scenarios where the system can get positive training data by simple trial and error, and it often struggles with more challenging cases. Learning from demonstration is an easy way to solve this problem, but however, it requires an expensive setup and an expert operator that knows how to control a robot, which makes it hard to scale up. So to address this issue, we make this very simple hardware device for collecting grasp demonstration. So this device made of a plastic grabber tool that you can easily buy from Amazon with $20. And we add a wrist mount camera to capture RGBD videos. So this device is designed to mimic the real robot's end effector with a very similar gripper and the same RGBD camera. So this hardware device provides a very low friction interface that enables untrained people to collect grasping data in almost any environment that's no longer limited by the robot's physical access. And because it is a human controlling the gripper, we are able to collect the data for very challenging tasks such as loading dishes in dishwasher, and without worrying about the robot's failures that may lead to broken dishes, for example. And finally, since the gripper tool is designed to mimic the real-world robot and effector and sensor, the data collected here is much easier to transfer to real robots. So in total, we collect more than 7,000 trajectories, and we can compute the full 6-step pose trajectory of the end effector by using 3D reconstruction. So now we have the data. The next question is how to enable efficient learning from this data. So again, this task is given a current state of the environment represented as an image. We want the system to predict where to move next and eventually lead to a successful grasp. A critical component in this problem formulation is the choice of action representation. Many recent work choose to represent actions using continuous values that hold abstract meaning, such as the end effector offset or joint angles. The issue for this representation is that the mapping between the action and their corresponding effects on the state need to be explicitly learned, or in many cases memorized by the network, which will make the algorithm very hard to generalize to new state and action pairs. Instead, here we use a new action view representation where each action is represented by the prediction of the next state, assuming the system took this action. In this case, the network only needs to look at all the possible next states and find the ones that's most promising in order to execute the corresponding action. So using predictive model for robot control is a common way to improve the learning efficiency. However, the challenge is always about how to obtain an accurate predictive model for all possible actions. So in this work, since the action is represented as a state of motion, and as the camera is rigidly mounted on the robot's end effector, we can use a simple view-based rendering as a proxy for the predictive models. So we call this approach action view representation, where the action and its effect on state is explicitly modeled through view rendering. So the system works as follows. As the end effector approaching the target object, the wrist-mount camera continuously gathers a new observation of the environment and aggregates them into a complete 3D scene representation using truncated sine descent function. And then, given a set of possible actions to take, we'll use a view-based rendering to simulate the future state with respect to different actions, where each view is rendered as if the robot's end effector moved according to that action. So by evaluating this state using a learned value function, the algorithm is able to select the best action that will maximize the total reward for the grasping success. The system is first pre-trained with human demonstration data and then fine-tuned with the real-world data. This process will continue until the grasp condition is reached and the robot will close its gripper to execute the grasp. So the idea of using view rendering as a predictive model actually can be applied to many other tasks beyond grasping, such as navigation or autonomous driving cars, where the action will directly lead to egocentric camera motion. And of course, the model can also be improved by using more advanced learning-based visual predictive model that considers other properties of the environment. So here I'm going to show you some experiments with our grasping system. We first test our algorithm across different scene configurations, such as tabletop picking, horizontal picking from a vertical wall, and other configurations. Since our grasping formulation operates with full 6 degrees of freedom, the same model works out of the box in all these configurations. And since our algorithm is closed loop, it's also able to handle dynamic environments with moving objects. And here are some numbers and comparisons to other state-of-the-art grasping algorithms. So to quickly summarize, in this project, we show how we can use affordance prediction to achieve generalizable grasping and how to use a new action view representation to enable efficient learning of high degree of freedom closed-loop grasping. As we know, grasping is only part of robot manipulation, and there are many more complex tasks, such as object assembly, that require the system to not only pick up the object, but also precisely place the object into its target location. And then in this case, although the system can easily pick up the object from any of these grasping points, without more detailed information about the object, the system will not be able to know how to precisely place the object in order to fit into the target location. This requirement speaks to a general group of tasks that are called kit assembly, where the goal is to precisely place a set of objects into their tight packages in order to form a single unit. And here are a few example kits that's really common in our daily life. So traditional robot assembly systems often heavily rely on accurate object pose estimation, which requires objects 3D model and expensive manual tuning for each kit unit. So does it mean that we need to go back to pose estimation pipeline again? Well, the main reason that's why this system cannot be applied in real-world applications is because of their requirements on object pose estimation. Because in many real-world applications, these kits are constantly changing due to promotion or seasonal event, which can happen as often as every 2 months. Therefore, it is not cost-effective to re-engineer the full assembly pipeline in order for every single object. As a result, a large portion of these everyday consumer packages are still manually assembled by human hand. Therefore, the goal of this work is to develop algorithms that can immediately generalize to new objects without the need of accurate object models or their sixth-of poses. So we present an algorithm called Form2Fit, which demonstrates that by learning the general concept of how things fit together, the algorithm is able to immediately generalize to new objects and kits as not seen during training. So here are two key ideas that enables us to achieve this goal. So first is that we observe that across many assembly tasks, the object's 3D geometry can often provide a strong cue on how they should be interconnected. For example, we can easily figure out which objects goes to which slot by just using their 3D geometry. And to implement this idea, we formulate the kit assembly task as a shape matching problem, where the goal is to learn a dense shape descriptor that directly establishes the correspondence between the object surface and their target placement location from the visual input. And second, we observe that it is possible to acquire a large amount of high-quality shape correspondence data for assembly by allowing the system to automatically disassemble them. It is possible because we know that in many cases, disassemble an object is much easier than assemble them. To implement this idea, we designed a self-supervised data collection pipeline through disassembly. By rewinding the disassembled sequence, we can obtain the ground truth labels for assembly. Here is a video showing the data collection process by using disassembly for different objects. To make the disassembly process easier, we fix the kit to the table to prevent accidental displacement from bad picking attempts. To make the disassembly process easier, we fix the kit on the table in order to prevent accidental displacement from back picking attempts. The core component of Form2Fit is a two-stream matching network that learns to infer geometrical correspondence for the object and their target placement location from visual data. Since these descriptors are orientation sensitive, they allow Form2Fit to infer how to pick and rotate the object before place it in the target location. Here I'm going to show you the system in action. So first, while the system is trained with objects that has a fixed position and orientation, it is able to generalize to different initial configurations with 90% of success rate. Second, while the system is trained with a single object, disassembly data, it is able to generalize to new scenarios where there are combinations of multiple and different kits. Finally, we test Form2Fit on the novel objects that are not seen during training. So by using the learned shape descriptors, Form2Fit is able to assemble those new objects with over 86% of assembly accuracy. So now we are going to take a closer look on the learned descriptors and see what does the network learn. So here we show the t-SNE embedding of the learned feature representation, where a similar color indicates closer feature distance. So from the visualization, we can see that the descriptors learns to encode rotation information, since the same object with the same orientation will share similar descriptors, and objects with different orientation will have different descriptors. Also, the network learns the spatial correspondence, since the same point on the same object will share similar descriptors. And finally, the network also learns to encode object identity, since different objects will have very different feature encoding. Here I'm going to show you some of the typical failure case of the system. First, we limited our action space to be top-down only, which means that the system will not work for all assembly tasks. And if we're able to combine this system with the sixth-of closed-loop grasping approach we described earlier, then we have the potential to extend this work to support more complex 3D assembly tasks. Second, our system also has trouble handling transparent objects. In some cases, we need to spray paint the object in order to make it visible to the depth camera. So to address this issue, in a parallel project, we try to study how to use machine learning and synthetic data to estimate the 3D geometry of transparent objects. And here is the example results of the system called ClearGrasp. And you can go to the project webpage to find out more details. To summarize today's talk, I have talked about two works that enables generalizable manipulation, one for generalizable grasping and the other for generalizable assembly. In both cases, we consider two important questions. One is about how to choose the right visual representation for given tasks, and the second is how to obtain the training data for learning this visual representation. So to enable the generalizable grasping, we use action affordance to directly map the visual observation to possible grasp actions. And we also use action view representation to enable high degree of freedom closed-loop control. And we train this model with low-cost human demonstration data. To enable generalizable assembly, we study the idea of learning shape correspondence for object assembly. And we train this shape matching function from a self-supervised disassembly data. Finally, I would like to thank all my collaborators and funding agencies, and also thank you for listening.